Welcome to my channel. My name is Lohit and I am currently pursuing my BTech in EC with a specialization in data science at SRM Ramapuram. Today, I will be presenting the project I built during my internship at Emertxe, a real-time EV dashboard and ADAS warning system built on the STM32 Cube IDE embedded platform. Project overview. This is a dual purpose embedded system. On one side, it monitors the EV state, things like state of charge, battery voltage, and fault flag. On the other side, it acts as an ADAS layer, watching for blind spot hazard, potential collision, and overspeed condition. Both of these run on the same STM32 microcontroller. So instead of needing separate expensive modules for battery monitoring and driver assistant, we bring both together on one affordable chip. Problem statement. There are three problems I wanted to address. First, drivers often don't get timely alert about nearby obstacles, especially in blind spot or during low speed maneuvers like parking or lane changes. Second, EV drivers today usually just get a battery icon on the dashboard, not real continuous visibility into state of charge or fault condition. That's not enough information to trust the vehicle. And third, commercial ADAS modules are expensive, which puts them out of reach for entry level EVs. My goal was to show that a low cost microcontroller unit based system can bring core safety features to vehicles that otherwise wouldn't have them. So why did I choose ARM Cortex M3? The ARM Cortex family has three branches, each meant for a different job. First one, Cortex A, is a high performance core that runs full operating system. Think smartphones and infotainment system. Cortex R is built for deterministic hard real-time tasks like automotive braking system. And Cortex M is the low power low cost core designed for deeply embedded, always on control, used in IoT nodes, sensors and motor control. For this project, I chose the STM32F103C86 Blue Pill, which is built on the ARM Cortex M3 core, running at 72 MHz. It gave me the right balance of real-time responsiveness, low power draw, and low unit cost, exactly what this application needed. So the key system features. So these are my few key system features and others will be shared during my code. So top speed is 20 km per hour. Ultrasonic range maximum is 400 cm. Maximum SOC level is 100%. Maximum temperature threshold is 120%. Maximum brake input is 100%. And a regenerative torque of 80%. Hardware components. On the hardware side, the heart of the system is the Blue Pill board, which handles sensor polling, ADAS logic, and UART telemetry. Around it, I use 3HC SR04 ultrasonic sensor for front, left, and right distance sensing. For timing, TIM2 handles precise pulse width measurement for the ultrasonic echoes. TIM1 triggers potentiometer reading every 10 milliseconds and TIM3 triggers ultrasonic sensor reading every 100 milliseconds. A UART interface streams live telemetry and warnings out to a serial terminal or dashboard, and the whole system runs on a stable 72 MHz clock using an HSC pulse PLL configuration. Toolchain. For development, I use STM32 Cube IDE for firmware development and on-chip debugging. Before touching Python, I use picsimlab for circuit and firmware core simulation. Terraterm let me monitor live UART telemetry and help to chat with the microcontroller. For help, VSPE created virtual COM port pass for PC side testing and a Python based dashboard visualized the live telemetry on the desktop. So these are my board pin configuration which I have been set up in the microcontroller. The ADC inputs are PA0 as acceleration, PA1 for the brake pedal, PA2 for SOC, and PA3 as motor temperature. System core as PD0, PD1 as RCC oscillators. Connectivity USR to 1 for PA9 for TX pin and PA10 for the RX pin. Ultrasonic sensor ranges from PA0 to PB5 pins, where trigger pin is PB0 front, PB2 left, and PB4 right, and echo pin is PB1 front, PB3 left, and PB5 right. Blind spot indicators: PB8 for the front collision, PB9 for the left blind spot, and PB10 for the right blind spot, which is being showed in the LED, and fault indicator PB11, which is being showed in the LED. System architecture. Here is how it all fits together. Sensor data. From the 3 ultrasonic sensors and 4 potentiometer, it continuously polled by the STM32. That data is processed on chip against safety threshold by the ADAS and EV logic, covering things like time to collision, blind spot detection, SOC fault, speed, and regenerative braking. The processed results are then pushed out as a structured telemetry over UART, viewable on a serial terminal or a downstream dashboard. Importantly, this entire pipeline was simulated end-to-end in picsimlab before I moved to the Python. Software workflow. The software flow follows 5 main steps. First, it initializes the clock HSC pulse PLL to reach 72 MHz along with GPIO, the timers, and UART peripherals. Second, it triggers each HC SR04 sensor and each potentiometers in sequence, capturing the echo pulse width. Third, it converts the pulse width into distance for the potentiometer and takes the value of the ultrasonic sensors and calculates the blind spot, collision, speed, brake, SOC, temperature and acceleration threshold, and etc. Fourth, it reads the EV parameters, SOC, voltage and fault bits from the monitoring routine. And fifth, it packages all of this sensor and EV data into a single frame and transmits it over UART. ADAS warning feature. On the ADAS side, the system offers 4 warning features, which are blind spot detection for the left and the right blind spot, where the speed should be greater than 20 km per hour and the distance should be less than 30 cm. Forward collision for the warning warning alarm. It sets a distance of less than 50 cm, and for critical alarm if the distance is less than 20 cm. And the time to collision, it determines the time to collision when the blind spot and the forward collision alarm is been on. And overspeed detection, when the speed of the vehicle is more than 120 km per hour, it increases the it produces a warning. Fault detection features. Over temperature. When the temperature of the vehicle goes beyond 90%, it automatically sets a fault. And state of charge. When the SOC drops below 5%, it produces a fault flag. And collision. When the front distance is less than 200 cm, it automatically produces a fault collision. And sensor timeout. When the sensor does not receive data for a time like 500 milliseconds of time. Challenges and debugging. Every project has its share of debugging, and this one was no exception. Early on, a TIM2 prescaler misconfiguration caused inaccurate pulse width timing. I resolved this by recalculating the prescaler and ARR value against the 72 MHz clock for microsecond accurate timing. I also ran into a clock source mismatch where the system was running on HSI instead of HSC pulse PLL, leaving it at a lower unstable frequency. Reconfiguring the clock source fixed that. The ultrasonic sensor also misread the target at a very close range. So I added minimum range handling and revalidated the reading in simulation. Conclusions and next step. To summarize what's been achieved so far, I have a stable 72 MHz clock running via HSC and PLL, accurate ultrasonic timing through TIM2, working 3-zone blind spot and collision detection, UR telemetry with a printf retarding and a computer end-to-end simulation in picsimlab. Looking ahead, my next step are to resolve the SOC, always zero bug in the monitoring routine, like a battery management upgrade like real coulomb counting or a dedicated BMS IC instead of a simple based SOC read, plus cell level monitoring for multi-cell packs, and move from simulation to physical hardware bring up, like adding live dashboard UI for telemetry visualization and more sensor fusion, like add radar or a camera with a Cortex A or GPU companion, and the CAN bus integration replace the augmented UR telemetry with the CAN, and extend the fault flag covering to include overcurrent and thermal condition, and finally field test the warning threshold under real driving condition. So this brings me to the end of my presentation. So now let us go to the STM32Cube platform. So as you can see, this is my STM32Cube platform, and this is my blue pill board, and these are the pins which I have told in my PPT which I have configured. And in system code I have clicked the RCC, analog as PA0, PA1, PA2, PA3, timers as TIM1, TIM2, TIM3, and in USR1 I set the baud rate as 1,15,200. Yeah, 1,15,200 bits per second, and the mode as asynchronous mode. And in clock configuration I have set at HSC, pulse multiplication as into 9, and pulse clock, and AHB prescaler as divided by 1, and ABP1 prescaler as divided by 2, and ADC prescaler as divided by 6. So for seeing a live dashboard, we need to create some .c and .h files. So we have created a common.h file first thing. So in common.h file, we initialize that echo mode is 0, normal mode is 1, and sport mode is 2, and the state parked equal to 0, state ready equal to 1, state driving equal to 2, state regenerative equal to 3, state fault as 4, and fault none as 0 cross 0 0, over temperature as 0 cross 0 1, SOC as 0 cross 0 2, collision as 0 cross 0 4, sensor timeout as 0 cross 0 8, and UART timeout as 0 cross 1 0, and we have initialized timer and UART and ADC configurations like HSC ultrasonic reading like front, left and right, and we have set the LED collision, blind spot and fault. So EV controller.h. So EV controller.h actually calculates the speed, SOC, temperature and motor torque which are all required by the EV vehicle. So first it has a variables, acceleration pedal, brake pedal, so on, as you can see here, which we are going to use in the main.c and EV controller.c. And these are the basic parameters which we are going to use, that are maximum torque is 150, battery capacity is 60, mass factor is 1500 and so on, as you see here. And we are setting echo as 14 and others as 18. So EV controller.h. So in EV controller.h, first we are setting the torque as for echo 60%, normal 100% and speed 130%, and we are ranking the potentiometer like acceleration as 0, brake as 1, SOC as 2 and temperature as 3, and the total ADC channels as 4. And before the simulation started, we are setting the basic parameters like SOC should be 100%, driving mode should be drive mode normal, motor temperature as 25, speed in kilometer per hour should be 120 and so on, as you see. And actually I have set it here 120 because we should check the over speed lag. If I kept it as 10 here, it will be taking too much time for the value to get 120. So next we are actually the potentiometer values are a 12-bit value which ranges from 0 to 4095. So for understanding purpose we are been converting into 0 to 100% for acceleration and brake, and for motor temperature we are converting into 120%. We are reading the ADC value and storing here, and we are converting it and doing this. And for SOC, first it checks if the SOC is full by the potentiometer, and then it does not upgrade the SOC. It uses a physics model to calculate how much remaining torque is being left. And we are defining the states of the vehicle, like state park, the motor torque should be equal to 0, regenerative level should be 0, and acceleration is greater than 2, it should go to state ready. From state ready it should go to state driving. If the brake pedal is greater than 5, it should go to state regenerative, or else it should go to state driving. And if there is any fault, it should go to state fault, and the motor torque should be 0 here. We calculate the motor torque, and when the brake pedal is applied at the regenerative state, it should calculate the regenerative level and the motor torque and acceleration and power in kilowatt and so on, using the physics based inertia model as you can see in the screen. So for reading the three ultrasonic data, we call the ultrasonic .h and .c file, where front 0, left 1, right 2 and count 3. And we are setting the constraint line minimum centimeter should be 2, trigger pulse should be 10 microseconds and so on. And we are defining the few variables like distance per centimeter and validator. So ultrasonic.c. First in ultrasonic.c we are initializing the pins like front what the pin should be, left what the pin should be, and right what the pin should be. And we are rolling the 16-bit rollover by initializing the TIM2 configuration. And then first before the simulation it checks that the distance centimeter is 400 and validate it to 0, and it gives the right, front and left all these values. And next it sets trigger pulse for 10 microseconds by setting it high, and then delay for 10 microseconds, and then setting it to low. And then it wait for the echo pulse to receive Y, and once it gets I, it automatically gives to the echo fall, and it waits for the it is echo rise, and it wait for the echo pin to get low, and once it is get low, the time is been stored in the echo fall, and the total time is been calculated by echo fall minus echo rise, and the distance can be given as this pulse us into the speed of the sound divided by 2. We are dividing it by 2 because the sound waves travel to and forth. We only need the one value, that is the 2 value, so we are dividing it by 2. And with this value we are doing it for all the 3 sensors. Next, ADAS. ADAS stands for Advanced Driver Assistance System. We have ADAS.h and .c file, where we set alarm none as 0, advisory as 1, warning as 2, as you can see in the screen, and the threshold like forward warning as 50, forward critical as 20, and blind spot distance as 30, as you see in the screen. And we are setting variables like front centimeter, left centimeter, right centimeter, as you see in the screen. ADAS.c. So in ADAS.c, first it checks for if any alarm is active or inactive using the if condition, and before the simulation it sets the front centimeter of the ultrasonic as 400, left right as 400, and time to collision as 99.9. and next it takes the value from the ultrasonic.c sensor and stores on the front, left and the right, and it calculates the speed in the meter seconds and the front distance in meter, and calculates the time to collision if the distance is less than 200. If it is more than 200, it automatically sets 99.9. and it checks for the forward critical and forward warning. For critical, the front centimeter should be less than 20 centimeter, and for warning the front centimeter should be less than 50 centimeters. and once it has been checked, it automatically gives the LED warnings. And next it checks for the left and the right blind spot. For the left and the right blind spot, the speed of the vehicle should be greater than 20 km per hour and the distance should be less than 30 centimeter. And with this help of this, we are creating a warning. If the collision warning equal to 2, that alarm priority is high. If the collision warning is 1, that is front is less than 50, we are setting it as alarm warning. And for left blind spot, right blind spot and overspeed, we are setting as alarm advisory. And if nothing is been given here, we are automatically giving alarm none. And if none of the condition is being satisfied, the LEDs are being resetted and been offed. Next we are going to do fault.h and fault.c configuration. So in fault.h and fault.c, we have none as 0 cross 0 0, over temperature as 0 cross 0 1, SOC as 0 cross 0 2, collision as 0 cross 0 4. And first it sets the fault flag as none and active equal to 0, and it updates the parameters of EV, ADAS and fault by the modules which we have used in .c of the every ultrasonic EV controller.h and ADAS.h. And next it checks if the motor temperature is greater than 90%. If then it checks the fault over temperature as OT, and if the SOC is less than 5%, it automatically set fault to SOC. And if the collision warning equal to 2, it gives fault collision. And if any of this fault is been not equal to none, it automatically sets active equal to 1 and state as fault state, and the light of yellow LED is being glown. And if the fault is been rectified, it should give active equal to 0 and state as driving, and the yellow LED is turned off. And in the UR.shell, if you type fault clear, these are the parameters it should follow, like state parked, active equal to 0, set speed kilometer per hour 0, motor torque 0, motor temperature 25. Next, UR.shell. So in UR.shell, we set the buffer size as 128 and command size as 64, and UR.shell.c. So first in UR.shell.c, we are setting the private handles as null, and in RB push function, we push byte by byte into the ring buffer, and in RB pop, we pull byte by byte as it moves in the RB push from the ring buffer, and we are transmitting into the UR terminal. And if you want to set the mode, you can automatically set as echo mode, normal mode, sports mode. And if you set wrong, it automatically sets do the correct mode and returns, and it does not do any modification. And we can set speed, SOC, temperature, obstacle, and we can even set obstacle clear, and we can even inject fault like SOC, motor temperature, collision critical and so on, and we can even clear fault clear. So this is my overall modules. So this overall modules is being called in the main.c function. So in main.c function, first we call the header files, and then we initialize the variables which we have used in the .h and .c files, and then we set the flag underscore EV equal to 0 and sensor flag equal to 0, and we are calling a variable message. So this actually flag EV is we are calling because we need to initialize that when it reaches a 10 millisecond, it should equal to 1, and if it reaches 100 millisecond, this should be equal to 1. And we set the private variables like a timer private variables, UART private variables, and we are setting the private function protocol by void protocol, static void protocols. And in int function, we initialize all the configuration and system clock configuration, all initialization, GPIO initialization and so on, and the EV, ADAS, ultrasonic initialization and fault, and this all is being given to a shell initialization. and the ADC values is been stored in the seed, and it is been injected by the and EV comma seed. And in while flag, if the flag EV equal to 1, it first sets it to 0, and then the value is been sent to the EV read ADC, and it is been updated with a precision of 0.01. And if plus plus EV underscore DV greater than or equal to 10, that is it prints every 1000 milliseconds goes to the print status. So in print status, this will only we will get in the UART terminal, that is speed, SOC, temperature, torque, acceleration, brake, right centimeter, time to collision, front left. At the start of the line, it prints speed, SOC, torque, temperature, right, acceleration, and brake. And in the second line, it prints the ADAS and fault like front, left, right, time to collision in second, ADAS collision warning, left or blind spot, alarm priority, and fault flag. And it's been pushed through the UART terminal. And we call the RCC configuration and so on, and we initialize the timers configuration and the UART configuration, like how much bandwidth we need. So this is my whole microcontroller setup. So now let us go to the simulation part. So as you can see in the screen, this is my simulation where there's 4 potentiometer for first one is for acceleration pedal, second one for brake pedal, third for SOC, fourth for temperature. This is the front ultrasonic, left ultrasonic, and right ultrasonic sensor. This is for collision front, left blind spot, right blind spot, and fault detection. And this is my virtual terminal. And in the virtual terminal, this is the output it is being shown, like speed, SOC, torque, temperature, right distance, acceleration, brake, front left right distances, time to collision, collisions, blind spot detection, alarm, and fault. And you can see here 121.7 km per hour. It's actually alarm advisory, but you cannot see here anything. We can actually see it in our dashboard. So for setting the dashboard, we go to the virtual serial port and we set COM2 for the picsimlab and COM5 for the Python dashboard. And then we need to go to the command prompt, and we need to call the function where it is been there, and we are setting it to the port COM5. So this is my dashboard, Python dashboard. As you can see, it starts with alarm advisory that it is over temperature over 122, and you can see here torque, acceleration, brake, motor temperature, alarm, fault, signal is being on, and speed history. From the starting till now, it shows what is the kilometer per hour it is been traveling, and this is the ADAS bird eye view, and this is the battery, and this is the range, and this is the mode, that is normal mode, eco mode, or sports mode. And if it goes less than 120, it automatically this alarm is been offed. Yeah, now it become 119, and as you can see, the alarm is automatically gone. So now let us check the front collision. So front collision, if the front collision is less than 200 centimeter, it automatically triggers collision warning and the fault detection. And you can see in the dashboard it triggers a critical alarm and a fault of 0x01. And if it goes beyond 200 centimeter, the automatically the red and the yellow automatically goes off, as you can see. And here the alarm is being gone and the fault is now 0x00. Now let us check for the right blind spot. If it is less than 30 centimeter, it provides an advisory alarm and no torque is being changed. As you see before, the torque has been sent to 0, but here the torque is the same and it just gives the advisory alarm. If it is more than 30 centimeter, it automatically that advisory alarm will be gone and the green light will be offed. And here the left one, if the distance is 20 centimeter, the blue light it automatically gets on for the left blind spot. And here also is same, the blind spot left is being triggered with no torque change. And if there is a more than 30 centimeter, automatically that left blind spot is being offed and the advisory alarm is being removed, as you can see here. So next, you are actually seeing that before I was getting at 121 kilometer to 119 kilometer, the battery has been increased because I constantly applied brake, and this is a concept of regenerative braking. And now if the temperature of the vehicle is 25, if I increase it more than 90 degrees Celsius, automatically it produces a fault. Yeah, it's 81 now, so no fault is being now given. 96. See, it produces a fault of 0 cross 01 and no further torque is being given. And here you can see that a yellow LED is being glown. And to avoid this fault, we should decrease it so that the torque again becomes normal. Yeah, torque now again becomes normal, as you see in the screen. So for SOC, if you do any changes here, nothing will happen because we didn't create an ADC channel for SOC. So for that, first we should take here till 0 and then go to the microcontroller blue pill and then click on the reset. If you click on the reset, automatically it results a fault 0 cross 02, setting that no SOC is remaining. And you can see that a fault detection of this is been occurred. So this remove the fault, we should set the more than 0 value for the SOC and click on the microcontroller reset. So now you see that fault flag is been gone, and you can see in the Python dashboard that the full charge is been given to the system, because once full charge only the EV vehicle starts moving. So this is the end of my project. I thank the Emertxe team for giving this project during my internship. Thank you all for patiently listening to me.